Okay. So I hope everybody has seen the recording of my last class where attendance was not compulsory. So did everyone went through the go through the material?
Yes, sir.
Yes. But those two yeses seems to be, the people who were present there. Is there anybody who was absent in my last class and has gone through the materials, or at least has gone through the recordings?
Yes, sir.
Okay, fine. See,
Yes,
in my last class, yes.
Sir, I have some doubts, sir, in last class video.
I'll that linearization part through tangent line I'm again going to discuss today.
Before this, sir, I have some doubt.
Doubt on what?
In sir phase plane.
Phase plane, okay.
Yes, sir. If in a phase plane we have some two eigenvectors.
Okay.
If we do two eigenvectors, then sir, if we choose any other trajectory, is it possible it intersect with any of the eigenvector?
Any of the eigenvectors?
Yes, sir. Because in the last class, in some picture, I seen this.
Whether the trajectories.
Yes, sir.
Yeah, I think you should be able to answer that yourself. I think nowhere in any of the pictures I showed any of the trajectories intersecting with each other. Are you sure you saw something where?
Yes, sir. Yes, sir. I saw in the last class video, in the starting video, I think around 17 or 20, 70 or 20 minutes on.
Okay, they were intersecting. I mean, they were intersecting when I drew it, or I mean, it was a ready-made picture.
No, sir. In the blackboard, sir.
In the blackboard, no. They cannot intersect. I think you should be able to find the answer yourself. Like say, if they intersect, right? Then their intersecting point, say, suppose their intersecting point is say something like say x0, y0, right? So that means what is going to happen? Like say, if you use that point as an initial point, right? So then you are going to have two different solutions, isn't it?
Yes, sir.
Right? No, they're not going to intersect. No. I think the maybe I mean somewhere the way I drew it, it looked like intersecting. No, they are not going to. No. Right? See, in the like say in the class where I did the notion of stability, right? So if you look at that, I clearly told that like say when we were studying the population dynamics through logistic growth, so then there was a line, something like there was a line. If you recall, there was a line. This was say y equal to 0 and this was y equal to k, right? So then I told you that I think this was t, this was y. Okay. So then I told you that although the solution is going to evolve like this, they are never going to intersect with this line because of that uniqueness of the solution, right? So y equal to k is going to be an asymptote for all these solution emanating from some points along that y-axis, or I mean where it is the initial condition, right? So, but they are never going to cross each other. Okay, so they cannot. Okay, so that is the only doubt.
Yes, sir. Thank you,
okay,
sir.
Fine. Yeah. So I was in linearization and local stability. Linearization and local stability. So, what is it different from the stability of linear system is that? So here, what we are going to do, say, suppose eventually I want to get into this. So this is equal to something like p of xy and dy dt. So this is equal to something like q of xy. Okay. So this is an autonomous system. This is an autonomous system. Although, of course, it is a plain autonomous system. So right. So now, before moving here, so what I was doing in my last class. So I was showing you a one-dimensional problem. Okay. So what is the meaning of linearization? Although I explained it to you, I want to again repeat it so that the concept is clear to you. So the difference between the previous system and this system, where we considered a linear system, was that here P and Q they were linear in x and y. So this P and Q at most they were something like this: ax plus by, and this is cx plus dy. Okay. So now they are going to be nonlinear in x and y. So that is what the difference is going to be. So now the question is whether I can reduce P and Q into some linear expression in such a way that if I try to analyze the property of that linearized system, whether that linearized system is going to show the same behavior as the original system. Okay, so now let me come back to a function of one variable. Say, function of one variable. Say, suppose I am considering y as my dependent variable and x as the independent variable. So then, say, suppose at this particular point, I draw a tangent. So suppose this point, say this is y equal to, should I say, okay, fine. This is y of x and equal to. So suppose this point is say x1y. Okay. So then what is going to happen? Like say the equation of the tangent, it is simply given by this, right? It is simply given by this, or this is simply your y equal to y x1 plus y prime x1 x minus x1. Okay, fine. Now you can see that the yellow line, this yellow curve, the yellow is graph. This is a curve. So now what is going to happen? Like say I can approximate this y. I can approximate the function y by this expression. Okay. So what I mean by that? Say, suppose I want to find the value of the function y in the neighborhood of these points. So suppose somewhere here, say, right? So then the actual y is this. Right? But instead of if I what is going to happen if I approximate through this function, which is nothing but a linear expression in x, because you can see that here, see y x1 is constant, again y prime x1 will be constant. So this is simply going to give you this straight line, right? So instead of this actual value, it is going to approximate the value of y through this length. Is it okay with everybody? Right?
Yes, sir.
Isn't it? So now let me try to show you a picture. Okay. Say, suppose I'm trying to concentrate on this part. I'm trying to concentrate on this part. Okay. So if I take this figure, so say suppose it is something like this, and then it will look something like this. Is it okay? For the time being, it is okay, right? So now let me concentrate here. So suppose this is the magnified version of this. So then this part, what it is going to look like? It is going to look something like this. Are you getting my point? Isn't it? if I magnify this part, right? It is going to look like this. Is it okay with everybody?
Yes, sir.
Fine. So now let me come to this part. Now, if I want to magnify this part, okay. So my straight line, I mean, it being this part. So then it is going to be like this. It is going to be like this, isn't it? Right? Okay. What I mean to say is that means in the neighborhood of this point, very close to that point, the straight line approximation is going to be a very good approximation. Because now see, if I want to find the value of the function through this straight line, so then in the neighborhood of this point, they are going to give you almost equal values, isn't it? Is it okay with everybody?
Yes, sir.
Now, have you understood the concept of linearization? What is the meaning of linearization? Right? So basically what we do, you take any function. So what we do, we try to approximate the function, the value of the function at a particular point by a linear function. Okay, and it is not like that that linear function that you are going to do. I mean, you are going to draw a tangent exactly at that point. It is not like that. Okay. Say we are trying to find out the value of the function in the neighborhood of some point, and we are trying to approximate it through the values along this straight line. Now, obviously, you can see that as I move away from this point. Say, suppose I want somewhere here, exactly where the value is, right? So I am going to get a better approximation if it is somewhere here, isn't it? Right? Here it is going to give me better approximation. And again, if it is somewhere here, it is even going to be better, right? So this should give you an idea that as we move away from that particular point, right, through which the tangent is drawn, our approximations are going to be worse and worse. Is it clear now? Yes?
Yes, sir.
Right? So linearization is not simply some first degree. You shouldn't concentrate on the degree of the polynomial being one means linear. No, linearization, the physical meaning is this. That is what it is. Okay. So then those who missed my lecture, again I am repeating some of the stuff. So then what, because we already know how to linearize it. So now you know that, I mean, if I am seeking, say, suppose I am considering a one-dimensional problem. Say, suppose your x1 is a critical point. X1 is a critical point. So that means my function is going to be something like this. Your, say, x prime. So this is going to be equal to something like g of x. This is going to be something like g of x. So then what we are going to do, in order to find the critical point of this system, of course this is one dimensional, I will simply plug in g of x equal to 0, right? Okay, so then by solving this equation, if I get, say, x1 as my critical point, so that means g of x1 is going to be equal to 0. So, right? So now, if at the point x1, I draw a tangent. So then, what is going to happen? So this I can simply approximate as this is g prime x1 x minus x1, right? And since g of x1 is 0, this is going to simply give you g prime x1 x minus x1. So then if I plug in g prime x1 equal to lambda, so then you can see that you can easily solve this equation, and eventually by solving this equation you are going to get x as a function of t. This is equal to x1 plus c1 e to the power lambda 1. Okay, so that means the stability of the solution is going to depend upon the sign of this lambda 1. Okay, so you know that if lambda 1 is less than strictly less than 0, definitely this solution as limit t tends to infinity, this is going to go to x1, right? It is going to approach the critical point. Is it okay with everybody?
Yes, sir.
Right. So
Yes.
that is why what we do we simply conclude that there is a theorem that g prime x1 less than 0 implies x1 is asymptotically stable. Asymptotically stable. Okay, and obviously if this is greater than 0, so that means lambda 1 is greater than 0, it is going to be stable, right? So that's it. So now we are in a position to move to autonomous plane autonomous system. Okay, so now let us move to 2D. Okay, so now in 2D, say now let us consider a plane autonomous system as I have told you, Pxy and dy dt is equal to Qxy. Okay, and suppose your x1, y1, this is the critical point. This is a critical point for this system. Is it okay? Fine. So what does it mean? What does it mean? That means your P x1, y1, this is equal to 0. Similarly, fine. So far so good. Fine. So now earlier what we did, we had a tangent line approximation. The linearization was done through tangent line. So now let us see what happens. Okay, fine. Say, suppose I consider a function of two variables, right? So the graph of a function of two variables is a what? Graph of a function of two variables is a what?
Surface.
Surface, right? So suppose I am considering a function of two variables, say x and y, right? And then suppose, like say j equal to some function of f of xy, right? Along j, I'm designating a value of a function f of xy. So then what is going to happen? Like say it is say suppose it is something like this. It is a surface. It is a surface. Okay. Now suppose maybe you should think that the surface is going to do something like this. Yeah, I can have a surface. Okay, fine. Okay, fine. Say suppose at this particular point, I want to approximate the value of the function. So like before, what I'm going to do here, I'm going to draw a tangent line here. I'm going to draw a tangent line here. Okay. See, you can think about this say parabola. Z equal to x squared plus y squared. Right? Is it a parabola? Yes? Yes or no? It is going to look like this, right? It is going to look like this. Fine? For this. So that means your this xy plane is a tangent plane to xy plane is a tangent plane to this surface at the point 0, 0 at the origin. Is it okay? Fine. So now, as before, what is going to happen? If I draw this tangent plane, then you know that if I designate this function be equal to f of x, right? So the equation of the tangent plane at the point, say, at the point x1, y1, x1, y1, and if j1 is the point corresponding to x1, y1 to the surface. So that means I am seeking a tangent plan at the point x1, y1, j1. So then the equation of the tangent plan, equation of the tangent plan at say j1 is given by what? J minus z1 equal to fx at x1 y1 into x minus x1 plus fy at the point. Definitely, I'll come back to this stuff again. I'll have to when I'm going to teach you partial differential equation. So this is going to be an integral part of that. Okay. So this one is fine with everybody, right? Is it okay?
Yes, sir.
Yes.
Yes, sir.
So that means this is going to be so this implies say j. If I want to approximate the values of the function z equal to f of xy, equal to f of xy through the tangent line approach. Like say for this yellow surface at this point, if I want to approximate it in the neighborhood of this point, I will use this equation. So this as a function of xy. So this is equal to like is it okay with everybody? Is it okay with everybody? See, basically what I have done, the function f of xy has been approximated by this function. Is it okay? Fine. So this is going to give me the linear approximation for a function of two variables, and this is also called the tangent plan approximation. Now, is it clear? Because the concept is the same. So what is going to happen in case of a tangent plan? In case of a tangent plan, you are going to have this scenario. You are going to have this scenario. Okay, are you getting my point? Like suppose, I mean at this point to this surface, I am drawing this tangent line, right? So now if you magnify this spot, so then see the surface is looking flatter and flatter, right? So that means in the neighborhood of this point where the tangent line is being considered, right? The tangent line is a very good approximation of the given surface. Is it clear to everybody? Right?
Yes, sir.
Yes. So that is what exactly we are doing here. So this is the geometrical interpretation of that. Okay. So that means now let me come back to the plan autonomous system. So here now look at these two. Okay. I think I can erase this. So you can easily remember this. So now, like say, if for the function p of xy I do this, so simply what is going to happen? The tangent line approximation, I can still write it as j of xy. Tangent line approximation would be given by this. So this is going to be the derivative of p. Simply, it is going to be this. Is it okay? Fine. Now, the only difference is that here, x1, y1 being a critical point, the value of this expression is going to be 0. Fine? Clear? Is it clear to everybody?
Yes, sir.
Right? So that is why, now let me come back to this. So this is my original system. This is my original system. So now you know that in the neighborhood of the critical point x1, y1, this can be approximated as your px x1, y1, x minus x1 plus py x1, y1, y minus y1, and of course the value of the x1, y1 is equal to 0. That is why I can straightforwardly write this. And similarly, this is qx x1, y1, x minus x1, py y1, y minus y1. Fine? Okay. So now see, this is my original system, which is non-linear, right? And this one is the equivalent linear system. Is it clear to everybody? Because say here they are going to give you some linear expression in x and y. Because with this one, eventually it is going to give you something like, I mean, p1x plus p2y, isn't it? Is that? No. Okay. Now not p1x, p2y. Okay. Let me keep it like that. Obviously, it is going to give you something like p1x minus x1 plus p2 y minus y. Obviously, similarly, this is p1 x minus x1 plus p2 y minus y. Okay, fine. So that means the equivalent linearized system in matrix equation, I can write it as say xy prime. Okay, so this is equal to your px x1 y1, py x1 y1, qx okay, and then here your x minus x1, y minus y1. Is it okay? Fine. Till now you have understood, right?
Yes, sir.
Okay, fine. So now if I write down this matrix as say A, this matrix as A, this one. So then I mean this is simply x bar prime, okay, and then this is A and this is x bar minus x1 bar, right? Where I mean your x1 bar is nothing but this fix. This corresponds to the critical point x1 bar. Is it okay? Is it okay? Fine. And
Yes.
this A, it is also written as this. I mean G prime x1. Huh? It is also written as this sometimes. I mean in G they have written as G prime x1, but you simply remember that A is nothing but the matrix of the Jacobian. See now if you look at this, if you look at this expression, if you look at this expression of A, if you want to find out the determinant of the matrix A, so then determinant of A, this is simply going to be the Jacobian of P and Q with respect to x and y, isn't it? Is it okay?
Yes, sir.
Right? So that is why this matrix is called the Jacobian matrix also. Okay, so you know the meaning of this, right? So now let me concentrate here. Let me concentrate here. So I'll give you the summary. I'll just show you in slides the summary so that you don't miss it. We can revise it again. Don't worry about it. Okay, fine. Say this left hand side, this can also be written as like this, isn't it? Yes? Is it okay?
Yes, sir.
Yes, sir.
Right? Because x1 bar being a fixed vector, constant vector, the derivative of that is going to give you 0. Fine? So that is why I can write it as this as well. So if I substitute for this simply the vector h bar, so this is going to give me h bar prime is simply ah. Right? Isn't it?
Yes, sir.
Yes, sir.
Right?
Yes, sir.
So basically what happens, see, here in the a plane autonomous system, which was non-linear, and we have converted it into a linear system, right? And see, before converting it into a linear system itself, we assume that x1, y1 is a critical point. Remember, the critical point didn't come from this equation. Critical point didn't come from this equation. Okay, we already had assumed that x1, y1 is a critical point, irrespective of whatever happens. It came from simply equating the right hand side of the system of equations to 0. That's it. Okay. So now what is happening here? What is happening here? That your x1, y1 being a critical point corresponding to the vector x bar, it is equivalent to 0, 0 being a critical point corresponding to the vector h bar, isn't it? Is it okay?
Yes, sir.
Right? So now, if you simply like find out the characteristic equation and the eigenvalues, all the eigenvalues, right? So then corresponding to the point 0, 0 for h bar, you'll be able to find out all the properties, isn't it? You'll be able to find out all the properties, whether it is going to be stable or unstable, right? And that is going to correspond to the critical point x1, y1 for the original system. That's it. That is what we are going to do. But there will be some subtle difference, and I'll tell you why those differences will come. Why those differences is going to come. Okay, so let me first summarize. I'll just show you that in slide, and after that, where this linear system and non-linear system differs. I'm going to tell you that. And I think if you look carefully, although I'm moving pretty fast, if you really go through the stuff, then you'll be able to find that out. Okay. So, okay. So this is the Jacobian matrix. This is the definition of Jacobian matrix. So this I had already explained to you. So that tangent line approach. Okay. So this is the approximation. This is the approximation. Okay. So then the original system, this may be approximated in the neighborhood of the critical point x1 by the linear system this. I have already explained you. So this is the matrix A, and this matrix is called the Jacobian matrix at x1 and is denoted by G prime x1. I mean, it is up to you. Like, I think you should, like say, adhere to the original. You try to remember it like this. Okay, as I have told you, if and then I have made a transformation, and eventually this is what happens. This is what happens, right? So then, what is going to happen for this system h prime equal to ah? If there is an eigenvalue with positive real part, then definitely 0 is going to be a critical point, unstable critical point, right? So similarly, the negative real part, it is going to give you a stable critical point. 0 corresponding to h. So that means x1, y1 is going to be a stable critical point for, negative eigenvalues of A, right? So similarly, for positive real parts, it is going to be an unstable critical point. Okay, fine. So far we have made comments only about stable and unstable. We still haven't made any comment about their shape, how the shape of the solutions, of the shape of the trajectories, corresponding to that particular critical point is going to look like. Okay, fine. So now let me I'll do stability analysis, and then after that I'll go to the summary in T delta tau delta plan. Okay, so this is the theorem. I have already told you that see, you just simply try to connect it to the one-dimensional case, where I had g prime x1, I had taken that to be equal to lambda 1, and depending upon the sign of lambda 1, we had a over there we had an asymptotically stable critical point and unstable critical point. So similar to that, here, if the eigenvalues of A equal to this have negative real part, then x1 is an asymptotically stable critical point, and if it has an eigenvalue with positive real part, then it is an unstable critical point. Okay, so now this classifying critical point, I'll come to that later on, right? Based on whatever we have, let us try to find out. Let us try to find the stability of a system given by these two equations. Then you will understand. We do one particular example. Okay. Okay, so firstly, you have to find out the critical points. In order to find out the critical points, what you have to do, you have to plug in, the right hand side. So this part, this is nothing but pxy, right? And this is nothing but your qxy. Okay, so if I plug in pxy and qxy 0, just a minute, is it? This is y squared. This is y squared. Okay, so now, see, the second equation gives you x plus y equal to 0. So that means your x equal to minus y, right? So first equation is going to give you minus y minus 2y minus y squared. So this is equal to 0, right? So from the first equation, you are going to get y to be equal to 0 and minus 2, right? Yes? Fine? Okay?
Yes, sir.
So from the second equation, if y equal to 0, your x equal to 0. If y equal to minus 2, x equal to what? 2. X equal to 1. Simply 2, right? X plus y equal to 0, right? Are you getting my point?
Yes, sir.
Yes. Okay. So basically, what we have got 0, 0, and 2 minus 2 are my critical points. 0, 0, and 2 minus 2 are my critical points. Okay. That part is done. That part is done. So we have found out, say, maybe 2 critical points. This is x1, this one, and this is x2, this one. Okay. So now let us try to find out the Jacobian matrix. So the Jacobian matrix, your J. So this is going to be what? 2 minus minus 2y, and this is 1, 1, right? And the Jacobian matrix at the point 0, 0. This is what? 2, 0, 1, 1. Right? And Jacobian matrix at 2, minus 2. This is what? 2, 4, 1, 1. Am I okay?
Yes, sir.
Fine. So now let us try to find out the eigenvalues of this matrix. Okay. So that means lambda square minus tau. This is 3, right? Okay. And delta is 0. So this is equal to 0. See, here we have an interesting system. I'll come back to this at certain juncture. So this is going to give you your lambda equal to 0, 3. Right? Okay. So for lambda equal to
Sir, I think lambda is eigenvalues are 2 and it's 1.
So determinant is 2.
Okay, determinant is 2. We haven't considered that case.
okay. I was looking at this. Okay. So minus 3 lambda, then plus 2, right? Plus 2. Okay?
Yes,
Fine.
sir.
So this is equal to 0. And so this will imply lambda equal to 1, 2, right? 1, 2. Okay? Fine. So now, if lambda equal to 1, then your a minus lambda I. So this is going to, but anyway, so from here itself, I can say that because you know how to find out the eigenvalue vector. Simply, here you have got lambda equal to 1 and 2. So both t, I mean, it has a positive real part, isn't it? Of course, this is a real number. Then I mean, eigenvalues are real here, right? So that what is going to happen? X1, that means 0, 0 is an what?
Unstable critical.
Unstable critical point.
Unstable.
Still we haven't talked any, yes. Still we haven't talked anything about the shape. Remember, we still haven't talked anything about the shape. Okay, and again here it is going to give you lambda square minus twice lambda 2 minus 4. This is minus 2, right? Am I okay? Just a minute, Jay. These three entries are going to be fixed. I don't have to worry about it. So anyway, I don't have to do anything about it. I don't have to do anything about it. So just by simply looking at this, the value of the determinant, you can see that you are going to have real roots. Okay, one is going to be, I think, 3, other is going to be 1, minus 1. Okay, real roots with opposite sides. Okay, so definitely this is going to give you your what? A saddle point. X2, this is going to give you X2 as a saddle point. Okay, so and obviously here this is unstable. So again, it should give you an unstable node. Okay, so we are going to have doubt only on certain cases. I'm going to show it to you what certain cases you are going to have doubt. Okay, this is fine. Yeah. Okay. So now let me just try to interpret the critical points in your tau delta plane. In tau delta plane. Okay. Fine. I'll show you. I'll show you this slide and then I'll again come back to that. Okay. So this is about classifying the critical points. Okay. So now it is natural to ask whether we can infer more geometric information about the solutions near a critical point x1 of a nonlinear autonomous system from an analysis of the critical point of the corresponding linear system. Okay, so I'm going to show you this figure. Don't worry about it. Figure 10.3.7. But before that, you should know the following points. Again, you know that we have, 5 different kind of critical points, right? So they are going to be stable node, stable spiral point, unstable spiral point, unstable node, and 7. Okay, fine. And again, further you make sub-categorize them as center, and then if you have seen that corresponding to, equal, real equal, again there is what you have, one of the critical points, right? What happens? The trajectories are going to be straight line. So in that case, it is going to be degenerate, stable or unstable. They are also called stars, okay, because of their shape. Okay. So now this is important. The solutions have the same general geometric features as the solutions to the linear system. And again, this is very, very important. And the smaller the neighborhood about x1, the closer the resemblance. This I have already explained. Why it is likely to happen. Okay. So now let us see this case. Tau squared equal to 4 delta. You know that this corresponds to all points lying in the parabola. We had drawn it earlier. Right? You remember this, right? Isn't it?
Yes, sir.
Okay, just maybe let me let me do it here. I can definitely. Okay. This is tau. This is delta. Okay. I had a case like this. So this is tau squared equal to 4 delta. Okay. Say as before, obviously here in this particular region, this belongs to your what? This is complex truth, right? This particular region is complex truth, right? That is fine. So beyond that, here I am going to have your what? This part stable node, okay, and this part unstable node. That is fine. Okay. Now, and again here, somewhere here, I am going to have 7. Is it okay? Yes.
Yes, sir.
Right. So now let us concentrate here. Let us concentrate on the yellow line. So in that yellow line, tau square equal to 4 lambda. See, your lambda was what? Tau plus minus this 4 delta, sorry, by 2. Okay. So once this becomes 0, you are going to have equal roots, right? Is it okay? Fine, isn't it? So earlier
Yes.
in case of equal roots, I had degenerate, unstable node corresponding to this line here, in the positive tau part, isn't it? And similarly, if tau is negative, I will have degenerate unstable number. Sorry, degenerate stable number. Is it okay with everybody? Right? But now I'm not certain here. I'm not certain here. Remember, earlier what was happening? 0, 0 was my critical point, and 0, 0 was my critical point. And what happened? The original system itself was linear, but now the original system is not linear. Okay, so that is why I have some question mark here. Obviously, in this portion, it is going to be your definitely it is going to be unstable, and here in this portion it is going to be stable. But I don't know whether they are going to be node or something else. That I still don't know. Okay, because you see that it is the borderline of the real and complex eigenvalues there. Okay, fine. I'm going to show that to you in the summary. Okay, now another point is here. Another point here is that it is very interesting. If you look at this line, if you look at this line, if you look at this line, okay, this line corresponds to what? This line corresponds to what?
Delta 0.
This point line corresponds to delta equal to 0. So earlier we assumed that delta is strictly not equal to 0 because we wanted, why? In the linear system, yes. Why we had taken delta strictly not equal to 0? Because we assume that 0, 0 is the only critical point, right? Isn't it? Whatever system we had, we transformed it into something like what? Dx dt, dy dt. This is equal to ax plus by, and this is equal to cx plus dy, right? So we had taken AD minus BC not equal to 0 in order to get 0, 0 as my only critical points. Isn't it? Fine?
Yes, sir.
Right?
Yes, sir.
But here you can get multiple critical points, isn't it? You can get multiple critical points, right? And those critical points, it doesn't come from here. It doesn't come from here. Although we have linearized it, the critical points came from the original system itself, the nonlinear system. So there is no guarantee that you are going to have only one critical point. Is it okay? Fine?
Yes, sir.
Yes.
Isn't it? Isn't it? So that is why in the earlier case, whatever we did, that is why earlier system is sometimes called, degenerate. It is called degenerate. Okay. So that is why that unstable or stable node, that degenerate mode was there. Now you cannot take it. So this line I can still have critical point. Here also I can have critical points. Okay, for this line also I can have critical points. But again, it's a question mark. Okay, fine. So the next question mark is along this line. Next question mark is along this line. Okay, your positive delta line where your tau is equal to 0. So when tau is equal to 0, when tau is equal to 0 and your tau square minus 4 delta less than 0, then what happens? Tau is equal to 0. Obviously, here tau is equal to 0. Anyway, tau square minus 4 delta, 4 delta less than 0 means your complex root, isn't it? Right? Is it okay?
Yes, sir.
Fine. And
Yes,
tau
sir.
equal to 0 means
Yes,
purely
sir.
imaginary root. Fine? Purely imaginary root. Right? So earlier what we said that if it is And again say, not along this line, in this portion and this portion. Obviously here, in this portion, you are going to get stable, stable spiral. And in this portion, you are going to get unstable spiral. That is fine. Unstable spiral. Okay. But along this line, earlier we simply predicted that it is going to be a center. Isn't it? For purely imaginary, eigenvalues, it is going to be a center, right? But now, again, there is a question mark. You don't know whether it is going to be a center or stable or unstable spiral. That is what it is. Okay? So now, let us. I'll come back to the degenerate thing again. So this is what it is. See, this I have already told you. Tau square equal to 4 delta, tau equal to 0, the critical point. It is basically along that yellow line that I have shown, along that parabola. Okay. The critical point x1 is unstable, but in this borderline case, we are not yet able to decide whether x1 is an unstable spiral, unstable node, or degenerate unstable node. Okay. Likewise, like when tau is less than 0 also, they are going to be stable, but you still cannot directly categorize just by looking at further tests are required. I'm telling you. With some further tests, we may be able to we may be able to determine the exact behavior of the trajectories, but not every time. Remember that. So here, the critical point again, x1 is stable, but maybe either stable spiral, stable node, or degenerate stable node. Okay. So now again, if tau is 0 and delta greater than 0, right? The eigenvalues of A, this say it is pure imaginary, and in this borderline case, again, x1 may be either a stable spiral, an unstable spiral, or a center. Okay, fine. So it is therefore not yet possible to determine whether x1 is stable or unstable. That is what it is. Okay, fine. So now this is the, as I have told you, like this line is a doubtful case. This curve, this is tau square equal to 4 delta in this parabola. Again, along this, your imaginary axis, this is also a question mark. And throughout this line where delta is equal to 0, this is also a question mark. Okay, but we'll still try to answer some of the question marks along these three, this one curve and these two lines, like say, wherever possible, we'll try to solve that. Okay, fine. So, do I have no? Okay. So now let us try to work out some example. So that our understanding is going to be better. Okay, fine. I will do. Okay. So let me do one example. Let me explain Q. Okay. See, don't be afraid by looking at this second order equation. So what we are going to do, we are going to convert it into a first order. So this is called your Rayleigh's differential equation. This is called Rayleigh's differential equation. Okay. The first thing you have to show is that 0, 0 is the only critical point. This is the only critical point. Okay. So this is number A. So B is this 0, 0 unstable when this C stable. So then the next question is, when is it stable spiral? And B, you have to show that 0, 0, this is center when this is equal to 0. See, the given differential equation, it is a second order differential equation, isn't it? Right? So what we are going to do, we are going to convert it into a first order one. You know what the transformations are. So the very first transformation, what is that? Your x prime equal to y. Is it okay with everybody? Right? X prime equal to y. So then this is going to give you what? So x double prime is y prime. Is it okay? Fine?
Yes, sir.
Yes, sir.
Right? So for the other term, if I transpose it to the right hand side, it is going to give me, this is minus x and this is minus epsilon, and this is y cubed by 3 minus y. Okay, fine. So now, obviously, what is happening here? I mean, if I plug in the right hand side to be equal to 0, from the first one, your y is going to be equal to 0, right? And in the second one, if you plug in the value of y here, you are going to get x is equal to 0. Is it okay with everybody? Fine?
Yes, sir.
Right? So then we have already found out that 0, 0 is the only critical point. It is the only critical point. Okay? So the next one, again, you were told that, okay. So now, what we are going to do, we are going to find out the Jacobian matrix. So if I want to find out the Jacobian matrix, that Jacobian matrix, it is your, say, it is 0 plus y. So this is 0, 1, this is minus 1, and then what? Minus epsilon, then y squared minus 1, right? Okay, and obviously this at 0, 0, it becomes what? It becomes this. Am I okay? Yes?
Sir, there
See,
will be
epsilon.
one
Uh-huh.
in 2 position y square minus 1.
Y square minus 1, yes. Minus 1. So eventually it is simply going to be, simply at 0, 0, it is simply going to be epsilon, right? It is coming from minus epsilon y square minus 1. Is it okay? Fine? So, now your trace is what? Trace is equal to epsilon, isn't it? Right? So obviously, if the trace is positive, right? The critical point 0, 0 is going to be unstable. If it is negative, it is going to be stable. Is it okay with everybody? Isn't it?
Yes, sir.
Right? Okay. So this part is done. This part is done. Here the first part is done. So now your lambda, this is equal to tau. 4 delta by 2. Okay, so and I have already found out that tau equal to epsilon. Tau equal to epsilon. Fine. Tau equal to epsilon. Okay. So now I want a stable spiral. I have already in the second case, if tau is less than 0, I have already found out tau is less than 0. So and again your delta is what? Simply 1.
Yes,
Isn't
Yes,
it?
sir.
Delta is simply 1. So this lambda is going to be given by this. Okay. So now see, in order to get spiral, I need what? Complex eigenvalues. Isn't it? In order to get spiral, I need complex eigenvalues, right? So I want this to be strictly less than 0 because I don't want to get purely imaginary. I don't want to get purely imaginary one. So anyway, because epsilon is strictly less than 0, right? That is not going to happen. Okay. So now, for what values of epsilon I am going to get epsilon square minus 4 strictly less than 0? Obviously, your and then here what should be? Here, what should be there? In order to get this minus 2, right? Minus 2. Okay. So if this happens, I am going to get 0, 0 as a stable spiral. Okay. So now the last part is interesting. I would like to illustrate one more concept through that last part. Okay. The first three part is okay. First three parts are okay with everybody.
Yes, sir.
Right? Okay. So now let me come to the last part. So last part, they're saying that okay, when lambda equal to 0, epsilon equal to 0, prove that. I mean, your 0, 0 is a center. See, you can do that. You can do that by simply plugging in epsilon equal to 0 here. So that is going to give you x double prime plus x equal to 0, right? And from here you are going to get x equal to something like c1 your cos t plus c2 sin t, right? And this being periodic, you are always going to get a center, right? We could have done that, but here what I'm going to do, like say when when I have this spatial case, whether it lies here, or here, I have some problem, right? When eigenvalues lies along those, three, two lines and one curve, right? So in those cases, what we can do, we can try through your phase plane analysis. So here, what is done? You simply convert from the given equation. So dy dx. So this is simply equal to I think qxy and pxy. Okay. So then try to solve in terms of x and y by eliminating t. Okay. So then whatever curve comes out from there, you can have an idea what your trajectories are going to look like. Is it okay? Fine. So that is what we will try to do here. Okay. So here, obviously, okay, from here, but again, see here, I am getting something only in terms of x, isn't it? I am getting something only in terms of x, right? I cannot from here, I cannot exactly visualize the trajectory, isn't it? Fine. But if I go for this approach, so then what is going to happen? Corresponding to epsilon equal to 0, dy dx. So this is going to be here. If epsilon equal to 0, this is going to be minus x, and this is going to be y. So you know that by solving this, eventually you are going to get x squared plus y squared equal to something like constant, right? And that is nothing but a circle, right? So it is a center. Is it okay? It is nothing but a circle centered at 0, 0. So, right, 0, 0 is a center. Is it okay? Fine. So, and again, I am giving you one homework, and another one I am going to do. Okay, so here you have to classify each critical point as a stable node, your stable spiral, and similarly unstable node, unstable spiral, or a saddle. Like basically, you have to find out the nature of the critical points. Okay, so let me tell you that from here you are going to get probably 3 critical points. 0, 0, 1 by epsilon 0, minus 1 by epsilon 0. Okay, so then you have to categorize those critical points as amongst those 5s. Okay, stable node, stable spiral, unstable node, unstable spiral, or saddle. Okay, so now let me do another interesting example. It is x prime equal to y minus x squared. Okay, so the question here is you have to prove that this is a dynamical system, and again see dynamical system is nothing but whenever you consider a system like this, non-linear, under prescribed initial condition this, so these constitutes a dynamical system. Okay, so they are calling it a dynamical system. So you have to show that it has a unique critical point when alpha beta is greater than 1. When alpha beta is greater than 1. And further you have to prove that this critical point is stable when beta is greater than 0. Beta is greater. Okay, so that is, so here what will be the matrix A or J? Minus alpha, then x, then minus 2x, and minus beta, right? Minus beta. Okay. So before that, can you find out the critical points? Can you find out the critical points? See, from the very first equation, what I'm going to get? X into y
Sir, in the
minus
one
alpha, this is
position,
equal to 0. So obviously your x equal to 0, y equal to alpha, right? So when your x equal to 0, so then y equal to what? Fine, right? X, y.
sir, at the 1 position, it will be minus alpha plus y
Which one?
in the matrix A.
This one.
No, no.
Yeah, because with respect to x, and this is simply x. Okay, thank you. So here what is going to happen when x equal to 0? Here, if you plug in x equal to 0, y will be equal to 1 by beta, right? Okay. Yes or no?
Sir,
Yes.
Yes. Yes. What about the second one? What about the second one? Like when y equal to alpha? When y equal to alpha, so then your x square is going to be 1 minus alpha beta, right? X square is going to be 1 minus alpha beta, isn't it? Fine. And I have been given that alpha beta is greater than 1, right? So this is going to give you some negative, so this is going to be less than 0, strictly less than 0, right? But x is real, isn't it? Those variable x, y, they were real, isn't it? See, here these are not eigenvalues. I am trying to find out the values of x and y. So this case we are going to discard. Are you getting my point or not?
yes, sir.
Yes, because I have been giving that alpha beta is strictly greater than 1. So that is why this system has a unique critical point, and that is given by 0 and 1 by beta. 0, 1 by beta. Okay. So now at 0, 1 by beta, so this is what happens. Minus alpha plus 1 by beta. So this is 0, 0. This is fine. Okay. But anyway, I wanted to worry. I am not even going to say obviously here whatever happens, your that lambda is given by simply the diagonal entries, isn't it? Is it okay?
Yes, sir.
Fine.
Yes,
Lambda is given by the diagonal entries. So lambda equal to alpha plus 1 by beta and this minus beta. Just a minute, whether alpha greater than 0 is given or not. No, they haven't given anything. They haven't given anything. Okay, fine. So this again, I can write as your beta by your 1 minus alpha beta, right? Is it okay? And alpha beta is greater than 1. So the numerator is negative here. Numerator is negative. Is it okay? Fine?
Yes, sir.
Yes, sir.
Right? Fine. So that means if beta is greater than 0, definitely this is going to be negative. Fine? Okay? And beta is greater than 0 already makes minus beta negative. Right? So in either way, we are going to get a negative eigenvalue. Right? So that is why we are done. Like this critical point is stable when beta is greater than 0. Okay? Fine. Do I have 1 minute? No. Okay, just one thing I want to tell you about. Like say when your data is equal to 0, when data is equal to 0, so then what is going to happen? Your characteristic equation is going to be something like this, isn't it? Characteristic is going to be something like this. So your 1 lambda is definitely going to be equal to 0, right? And if the other lambda is non-zero, so then your solutions are going to look something like x equal to c1 plus c2 e to the power that non-zero lambda, say lambda equal to say r not equal to 0, lambda rt, and then y equal to something like c3 plus c4 e to the power rt. Okay, so from this, what we can do? If you want to eliminate your t, this is going to give you a straight line. You can easily check. This is going to give you a straight line. You can easily check. Okay, and again, what may happen? Suppose your r is also equal to 0. Your r is also equal to 0, right? So then, what is going to happen? Your trajectory is going to be simply a single point. Trajectory is simply going to be a single point. Okay. So here what happens if lambda equal to 0, right? Either you are going to get a single point or you are going to get trajectories as straight lines. That is what is going to happen. Okay. In case of degenerate system. Okay, fine. So from today onwards, I am going to start partial differential equation, and mostly I am going to use this book. I have already given you this, your Introduction to Partial Differential Equations with Applications by Jacobian and Thor. I don't know whether I'm pronouncing it right or not. Friends, I mean, may have different pronunciation. Okay, so from tomorrow onwards, I'm going to do that. Okay, so with that note, I'm ending today's class. So